we've covered a lot of operators in this lesson. And so what we're going to do now is we're going to have a case study, as always, to kind of wrap everything up and demonstrate how all these operators are going to be used. This particular case study, which is ex3, is going to examine the from callable, zip with, zip, flat map, do on success, subscribe on, then, and parallel thread pool operators. Do a bunch of interesting processing using these advanced features that come out of Project Reactor's Mono. And you can find this particular example at the link at the bottom of the slide. So what I'm going to do now, of course, is I'm going to switch over to my project in IntelliJ, and we'll walk through the code and show how everything works. So here we are in my Android Studio project for ex3 for Mono. Let's go ahead and take a look at the main entry point. This, again, demonstrates how to use all these different Mono methods and apply them in the context of a parallel thread pool. You can see here we have 3 methods that we're going to be registering with our async task barrier framework. So we register test fraction multiply async, test fraction combine 1, and test fraction combine 2. As always, all these things are going to start running concurrently in the background when run tasks is called, and they're going to run, and then we call block, and that'll have a single place to wait for all the asynchronous computations to complete. Okay, so now let's go ahead and take a look at Mono EX. This is where all the fun stuff actually happens. And the first thing we're going to do is we're going to define a local field that will have a random number generator. We need that for some of the code we're going to do down here below. Let's take a look first at test fraction multiply async. This is going to demonstrate how to asynchronously multiply big fractions using Mono flat map. So the first thing we're going to do is we're going to go ahead and make a big fraction asynchronously. So if we go ahead and take a look here, here's make big fraction async. It's just a helper method that is going to create a random big fraction asynchronously in a thread pool. So how does it do that? Well, it's going to use the from callable factory method. Recall that from callable is a lazy method, so that means it can be run in a background thread by using subscribe on. You can see here how we're going to go ahead and call our big fraction utils make big fraction factory method. Let's go look at that. So here's what make big fraction does. It takes a random number generator and a flag that says whether we're going to be reducing the big fraction or not. And the first thing it does is it creates a ridiculously large random big integer. So this is the number of bits, 150,000 bits for this random big integer. That's really big. Then we're going to go ahead and create a denominator, which is going to be the value between basically 1 to 10. And we're going to take that value of 1 to 10 and divide that into the numerator to create the denominator. And then we make ourselves a big fraction with the numerator and denominator, and then we either reduce it or not. In this particular case, we're going to reduce it, and that's because we're going to run this computation in the parallel thread pool. So notice how we're using the subscribe on method, that's the concurrency method, and we're saying, hey, I want you to run the computation from callable to the end in a thread from the parallel thread pool. Doesn't really matter which thread it is, just the next available thread. And then after we finish creating this, we're going to go ahead and have an action operator that will go ahead and append that to our string buffer so we can keep track of what was just created. Okay, so that's make big fraction async. You can see it's going to make a very big fraction. We then come down here after we've made ourselves this big fraction and it's being processed asynchronously. We're then going to come down here and say BFM1, which is this mono to the big fraction, flat map the result. And what that does is it says, wait until the computation for BFM1 is done, take the big fraction that's emitted from that, and then asynchronously multiply that emitted big fraction with this constant, which as you can see is a very large big fraction we created over here. And it says, go ahead and multiply that asynchronously. And by using flat map, you can see that the result of this will be a mono to a big fraction. If we'd used map instead, then we would have to have a mono to a big fraction. And I think you'll agree with me that that just gets unwieldy and kind of ugly. So here's multiply async. Check out how we do this. So we take these two very large big fractions, which are going to take a while to multiply. And again, we use our subscribe on trick. We say multiply BF1 by BF2, subscribe that to run, in the parallel scheduler. So again, that will also run in parallel. And then what we're going to do is when this computation is finished, we're going to go ahead and call the do-on-success method, which will display the mixed big fraction. And then we return the result from then, which, as you recall, is an empty mono. And that's used to synchronize with the async task barrier framework to say all those asynchronous computations are finished. If everybody else is done, then we can return from block. Okay, so that's the first method. Now we're going to talk about test fraction combine one. This is going to go ahead and asynchronously multiply and add big fractions using zip width. So this will be kind of interesting. In this case, we're going to go ahead and make ourselves two big fractions asynchronously, make big fraction async, get back M1, make big fraction async again with the random number object, we'll get back another mono M2. And then what we're going to do is we're going to go ahead and say when M1 finishes, we call flat map, when M1 is finished being created, go ahead and multiply M1 by this big reduced fraction that's a constant, and take the result of that and zip it with the result of taking M2, waiting for it to be done, and then doing an asynchronous multiplication there as well. So what's happening here is that we are going to basically multiply the result of M1 by this constant. We're going to take the result of M2 and multiply that by this constant. Both of those calls will take place asynchronously in parallel using that parallel thread pool that we talked about. And when both those calls are done, we will then go ahead and add the results together using the big fraction add method reference. So after we've done all those computations, then when it all succeeds, we're going to display the result, and then we're going to return then. So then, of course, as you will recall from earlier discussions, returns that empty mono to synchronize with the async task barrier framework. So this is a pretty cool way of doing all these computations asynchronously. That's the beauty of using flat map. That's the beauty of using zip width. We can get all these computations to run asynchronously, and it's very powerful. The third method here is called test fraction combine 2. And this is probably the most interesting of all the things we've seen so far. So now what we're going to do here is we're going to actually have 3 calls to make big fraction async. And as you can see, we have make big fraction async, first call, second call, third call. We stash these things away into local variables, M1, M2, M3. And then what we're going to do is we're going to create ourselves a combinator, or something that combines the results. We're going to call it a combiner to make it easier to pronounce. And this combiner is going to be a function which is an array of objects and a big fraction. And what it's going to do is it's going to take this big fraction array, and that's what it's an array of objects. And we say stream of, now we're using Java 8 streams just to show you can mix and match these technologies. We can say stream of BF arrays. This is an array of objects. And then we're going to go ahead and convert these objects from objects to big fractions using the map method. And then we're going to go ahead and use another method here that's part of Java streams called reduce. We'll talk about reduce in the context of RxJava and Project Reactor later, but in the context of Java streams, it's basically a way of taking the results of something in a stream and kind of pairwise multiplying everything together until you have a single reduced result. So what we're basically doing here is we're just going to add up all the results together. And we start out with an initial value of 0, and then we add all the results in the stream. So that's how we're going to combine all these results. Here's how this actually gets used. We create ourselves a mono to a mono array of big fractions. And then inside of this array, which we call async multiplications, we're going to go ahead and say M1 flat map multiply async, M2 flat map multiply async, M3 flat map multiply async. So we're going to multiply all of these big fractions in parallel using the parallel thread pool that we saw before. And all these computations are going to run asynchronously. Now, what we do at this point is we use mono.zip. So this is yet another variant of that zip combiner operation. And we take the combiner, which is this particular function up here, and we pass that in as the first parameter. And then we pass in the array of big fractions. We could also have written those computations in line, but I thought it was a little cleaner to use the async multiplications array. So what that's going to do is that's going to go ahead and do all these computations in the background in parallel. And when they all finish, we're going to zip them together by using the combiner to take all the results of those asynchronous multiplications and add them together. And I think you'll agree that this is really, really powerful. And it's also relatively concise. And it's a great demonstration of how you can mix and match different features in Project Reactor with things like flat map and map and from callable with things like zip and combinator and so on and so forth. So it's a really, really cool demonstration of how all these things work. And then when we're all done, we go ahead and display the results and then return then. So now that I've talked about all the different methods that are in this class, let's go ahead and take a look at what happens when we run it. I probably should have run everything first just to show how it all works. But basically what we're doing is we're calling various things in various orders. Now, this is what's interesting. First of all, you'll notice that we have some absolutely gigantic big fractions here. Look how large they are. This is what happens when you use that random mechanism that creates big integers with 150,000 bits of resolution and so on. You'll also notice, if you were to go back and take a look at this, that we actually called the test fraction multiply async method first. So that one was called first, but that doesn't finish first. What finishes first is test fraction combine 1, because it was doing less work. So you can see here that that runs in, that's printing the results in thread 27. You can see that the computations were actually done in a bunch of different threads. We're doing those multiplications in different threads. Here's the test fraction multiply async method. This is creating, as you can see, an absolutely gigantic big fraction, and this is occurring in thread 21. And this is going to go on for quite a long time. Once again, demonstrating the just absurd resolution you can get with these things. And then somewhere down here, it'll probably take a week of Sundays to get to, we'll find the results of the other computation that we were running in parallel as well. And that probably will take too long, but let's go ahead and test. There we go. So let's search for these calls to test. There we go. Test fraction combine 2. And this, again, as you can see, is running in thread 30. It's doing its computations in a couple of different threads. And as before, just look at the ridiculous resolution here. So lots of computation taking place. I'm very fortunate to have a very high-powered 8-core MacBook Pro with an obscene amount of memory and fast processors. And it's actually hyper-threaded, so it's got 16 effective cores. So there's a lot of things taking place. If you have a slow machine with few cores, this computation will actually take quite a long time to run. So at any rate, that's a quick overview of this example. Hopefully you found it interesting and useful, and hopefully it also teaches you and demonstrates the use of interesting mono operators.